Okay, first of all, to put up a little bit of context into this specific enabler, we are working with this enabler in the domain of dimensional quality. So, with this quality based on the specifications on dimensions, on lengths of manufactured parts or components. This area, called metrology or dimensional quality or whatever, is becoming a growing issue in the manufacturing domain. And the use of our specific enabler allows to use 3D point clouds that are a kind of file to control this dimensional quality. And this file is becoming increasingly important in different applications. Basically on, as I said, quality applications, reverse engineering, but also 3D printing related solutions. So all these different domains are working with a file called 3D point clouds. That is one of the key issues of our specific enabler. This is the principle of this kind of files is that we are changing into a new paradigm that is based on digitalizing real objects. Instead of measuring with contact systems, as we did a year before or decades before, now we are digitalizing real objects. So what we basically do is with normally laser technologies or scanner technologies, we scan a real object and we get is a 3D point cloud. Basically, these files, as you can see in the green one here, these files, what they do is they basically scan the surface of the real object, and they put a set of points, and then we can define density of points. I mean, a lower density of points or a higher density of points. It depends on the quality we need to do our particular application, and it obviously will generate a file heavier or lighter depending on the number of points. But what we do is to generate a set of points that they replicate the surface of the real object. And that obviously, sorry, is there any problem? Can you all listen to me?
Yes, yes, fine.
Hello?
Yeah, I can still hear you.
Okay, I just listened to something. I thought there had been an error or something. Okay, yeah. So as I was saying, this cloud of points replicates a number of points, and what they basically do is to replicate the surface of the object we are working with. This includes obviously the errors. If there are some dimensional mistakes in this part, we scan the object just as it is. So it obviously it has some advantages with respect to older technologies in terms of speed. Scanning speed is always, it tends to be faster than the other technologies, and in terms of accuracy, obviously. And as I said, we can use these files, these surface files, for many applications. The FITMAN specific enabler component is a component especially conceived to assist to the 3D digitalization of real objects. This specific enabler assures the possibility to manage this kind of files. We can store them and we can visualize them. These scanned images, as I said before, obtaining from real objects in the form of 3D point clouds. So, using hardware technologies outside of the scope of this specific enabler, we could scan real objects, and using this specific enabler, what we could basically do is to store it and visualize these files. Oh, one moment. Okay. So the capabilities of our 3D scan, more precisely, are to obtain accurate surface representations, as I said, and the 3D scan specific enabler is based on 2 different open source components that can be used independently. These open source components obviously are the storage module that allows us to store some parts, and the visualization module that allows us to visualize what we are actually scanning. As I said, these two main modules, these two main specifications of our 3dScan system, we can store and visualize precise scan images obtained from real objects. Normally, as I said, obtained by laser technologies or in some times other different scanning technologies. But we are always talking for this application in terms of hardware of non-contact scanning technologies. More precisely, the information that we can store in our 3dScan specific enabler is generated by the system, and then we have several outputs from after scanning these parts. We have the cloud of points, as I said, which is a set of points that represent the surface of the real object. We have a CAD model that we can also store. Normally, when we are working on components that we are in the manufacturing industry, we have CAD models that come from the design part of the factory, and they are real representations, obviously, of the components we should manufacture. These are normally on STL format. Then we have a mesh. That is, after obtaining a cloud of points, we should do some interpolations because we have a discrete set of points to obtain a mesh. And we can also store a comparison between the cloud of points and the CAD model. So a comparison between the real object we've got, the real object that has been manufacturing and we are now effectively controlling, and the CAD model that is obviously the ideal object, the object as it should be from a design phase. So this comparison in the form normally of a color mapping should put in evidence in which dimensional aspects the component is respecting the specifications of the CAD model. So this is all the different, let's say, files or type of files that we can store in our system. Then, as I've said, on a second step, with a different component of the same specific enabler, we can visualize these different files. We can obviously visualize the cloud of points as it is, as I showed before in the slide with the green part of the component. We can also visualize obviously the CAD model directly, the design model, and we could visualize also the comparison between the cloud of points and the CAD model, the color mapping. So we could visualize, as it puts here, the inputs, intermediate, and final results. And this allows us to have like a graphic image, very intuitive image of how our component is respecting the specifications or not. Let's go to the next slide. These are, from an architectural point of view, obviously the two components that we have are the same as I presented before. We have two main areas of the specific enabler, and this obviously is concreted into different components. From a format point of view, the 3D point clouds will be in ASCII format, while the deviation maps and the CAD models will be in STEP or in STL. This is a typical example of how we could use this specific enabler. Obviously, you can also think about other different configurations where the specific enabler could work. This is only a very typical or classical example of the use of the specific enabler on a typical manufacturing environment. I will explain by steps. So here we have the analyze part. That this is the part that we want to control, that we want to see if from a dimensional quality point of view is respecting what we should demand to our parts in terms of quality. So we use a scanning technology, a scanning sensor, to scan this analyze part. This produces obviously type of information, type of data. This goes into a module that is called a 3D point cloud processing. This does not belong to the 3dScan. There is another private component, and this will process the information obtained from the scanner technology. Into a point, in this other module of this part of the workflow, we have another information input that is a 3D CAD design that enters to be compared with information of the analyzed part. So then what we have is, in first place, we can store all this information. We could also store before the cloud of points, and then we can store the comparison between the 3D CAD design and the 3D cloud of points. So here we have the first moment in which our 3D scan specific enabler does some work, and then after storing all this information, we can visualize these comparisons. So here in the visualization model that also belongs to the specific enabler, we can visualize obviously all the intermediate results. So as I've said, we could visualize directly the 3D point cloud here, but we can also visualize the results of this comparison of the CAD design with the real part, real analyzed part. And this is the other module of our specific enabler. As I said, this center part is a private component that is out of scope of this presentation, although it is inside the FITMAN project. These are as a practical example of the results that we obtain that we can visualize with our 3D scan specific enabler. This is a real part. This is a component that belongs to a microwave. It's an helix from a microwave. So we actually scan this part, and we obtain a cloud of points. So here you have the representation of the surface of the microwave helix with a set of points after being scanned. And then once we have this, we should compare this set of points, so this real surface of this produced part, with the ideal model obtained from a CAD model of the design piece. And these are three examples of three different helix compared with their CAD models, with their ideal models. So what you can see here basically is a color mapping. That is the way that we call this format, that it's normally the comparison between two graphic representations. And what you can see is a set of colors. You have a color range, and what basically in the green areas, you can see that the produced part meets the dimensional specifications that were previously defined. Normally in the red parts is where the produced part, so the cloud of points, it's not really meeting what it was defined on the CAD model. So here in this part you have only some problems in this left part of the helix. In the middle helix you have a little bit more problems in the different corners of the different helix, and so you have on the right helix. So as I said, this is a color mapping, and it's based on the comparison of the helix, of the real helix, with a design model. And it's one of the main results that our specific enabler is able to represent. From a format point of view, there is actually one specific format for these color mappings, and our specific enabler is working with this format. Well, here you have the FITMAN catalog. As you said, as you can imagine, I figured that the rest of the specific enablers have already shown to you. The basic information that you can get from here, from the point of view of this specific enabler, is, well, here you have the 3dScan. You will get a little bit of basic information that will explain you basically what I've been explaining to you. I mean, what you get, what the specific enabler is intended to do. And then you have also the documents and the files that you should download to install this specific enabler. And you also have, I want to show you directly on the browser, and you also have technical information can be very useful to you, especially in terms of configuration, technical information in terms of installation, that is also in the FITMAN catalog. Is here in this one documentation. And here you have a little bit of detailed information, similar to what I explained to you from the point of view from an overview. It explains you the architecture from, a little bit more in depth. And then you have also useful information from an installation and configuration point of view. Here you have, a little bit of steps of an installation guide, and then a little bit of the typical interfaces you will find, how it works, to learn a little bit how it. Here you have a few examples. There is a mesh, and there is also a cloud of points. Well, as I've said here in this part of the FITMAN catalog, in the documentation part, you have a little bit more of details of the specific enabler. Obviously, if you have any doubt in terms of installation or how to integrate it with something, how to work, the quickest way to contact us, and we will try to do a little bit of user guide to help you to use this specific enabler. So I will finish only with one video that shows a little bit in live how this specific enabler works and how you should, it shows a little bit of examples in a dynamic way of what this specific enabler can do and can get.
Nowadays, the parts leave the production line and only some of them are measured in the metrology department. This means that among all the parts coming from the production line, we measure neither the 100% of the features nor the 100% of the parts that we manufacture. This statistical control is performed in the metrology laboratory, and as a consequence, some defective parts could be sent to our customers. 3D scanning is changing the way quality control is being performed and will be performed in the future. 3D scanning speeds up the dimensional and surface data acquisition process and allows for quality control to be performed close to the production line. 3D scan enables the storage of the generated 3D point clouds and results in the cloud, facilitating the collaboration between departments and factories all over the world. In order to achieve zero defect production, all the parts must comply with strict dimensional tolerances and surface requirements. The first step is to obtain complete information about the TRW part. The 3D scanning device is based on non-contact technology, which allows a fast capture of a huge volume of data. The system produces a 3D point cloud, a high-fidelity, high-resolution 3D replica of the physical part in the digital world. Each point in a 3D point cloud represents the surface coordinates of a scanned object. Using the 3D scan storage, the user can upload the generated file in the cloud. The component also allows the display of the 3D point cloud using a web browser through the 3dScan visualization. This functionality will enable TRW engineers, production and quality managers the interactive visualization within the information through web interfaces and from any device with internet access. The captured 3D point cloud are transformed into a mesh representation of the part made by geometrical figures. This representation is further processed and compared with ideal CAD models or reference models parts, providing the deviations between our actual manufactured parts and the reference dimensions. 3dScan also enables the storage and visualization of these results obtained in the analysis of real parts. We want to implement this system that will allow us to measure all the characteristics we may consider appropriate, guaranteeing that no parts with defects are delivered to our customers. This will increase the competitiveness of our factory and will enable us achieving our ultimate goal, a quality performance of 0 parts per million.
In this big data experimentation, Whirlpool is expecting to achieve a big step forward in the way how we are measuring complex geometries. This fan, taken as an example, is a part number that we are assembling in our ovens. If this part number will have the wrong geometry, the performance of our microwave and the way how our customer will perceive the quality of our product will be not okay. So using the traditional gauging, we cannot measure the geometry of this part number in the right time, okay, let's say in a few minutes. So we believe that the adoption of a 3D system that able to be connected in an IoT device could help us to provide three things. First of all, of an effective way how we measure our products and be able to address the issues to other factors that are involved with the manufacturing. An effective way to improve the capacity to filter the defects that we have in our processes, and a robust system to keep tracking the quality of our products over time and over years, achieving our goals of having zero defects.